It has started. So can you see the screen? PowerPoint.
Yes, sir.
So last time in the lecture we were talking about the steady harmonic response and what is the dynamic magnification factor and amplification factors for the damped and undamped harmonic motion, and the steady state harmonic response was studied. So the ratio of the harmonic response to the static response, there are three types of responses. One is the displacement response factor, that is RD. RD basically equal to this one, because this is the harmonic response and divided by the static response. So UT, the response due to the force vibration divided by the response due to the static load P naught. So this is equal to this one, and from that we extract the RD value, which RD is basically the coefficient of that part. Similarly, the velocity response, when we divide by the velocity u naught t, the coefficient of this part is velocity response, and the acceleration response factor, that is the further derivating this equation second time, and this is the acceleration response is this one is the acceleration response of the any system. So basically the displacement and velocity and acceleration are interlinked with each other in case of the this harmonic loading. So I told you about the four-way logarithmic plot, that you can plot all these three parameters on the four-way logarithmic plot. One is the one side is the frequency ratio, other side is the velocity response, deformation response, and the acceleration response. So these are also can be available as special log paper where you can show all these three parameters on a single logarithmic paper. And these are the frequencies at the resonance. The frequency basically at the resonance, the frequency ratio can be computed simply by uh, taking the response and then putting the value of beta such that first derivative or the second derivative is equal to, or the u value is set to the derivative of those values is set to the 0, and by applying the maxima function you can compute the beta d, the displacement resonance ratio, velocity, and the acceleration resonance ratio. The three dynamic factors, the response factor at the equal to this one, and by putting the beta equal to 1, these comes out to be this one at the resonance. So this is the resonant response for the frequencies. And the half power bandwidth is basically used to compute the damping ratio, where we take the value of this value at 1 by 2 under root of the resonant frequency. At the resonant, the peak displacement at resonance, we take the 1 by 2 under root of that, and those two values can be used to compute the uh, damping ratio. So that can be computed by taking those two values. Then I discuss about the what is the effect of the in case of the rotating machinery, the function, because in case of the rotating machinery, rather than the force P naught is basically me into omega square. So that P naught will be replaced by this parameter in case of the rotating machinery. The other things remains same, but in that case this thing is changed. Transmissibility was an important function that in case mm, you are applying some load and how much force is transferred to the mm, structure, or how much force is transferred to the ground. So let's say there is a ground motion. If there is a ground motion of the any system, that is given by, that can be written as the g sine of omega t. This is the ground motion. So taking the second derivative comes out to be this one. So although there is a no force in the system, but still due to the ground motion, of course, the total displacement will be mut, and that total displacement is due to the system vibration plus the ground motion. There are two kinds of the now displacement involved. So putting the values of these and taking the mug on the other side, this is it itself is basically the force ma. M into acceleration is the force, which is equal to this value. So putting the value of the ug here, you can get this value. So here this is mg. G is the basically the amplitude here of the ground vibration. Omega square is basically the frequency of the ground vibration, omega. And so in this case, this is the ut. This becomes the response of the system when it is subjected to the ground motion. Now the amplitude of this part is basically the g value. G is here, and this one, and sine omega t. So this part is what is g here, and what is gamma here. So g is here the given as the static, the peak ground displacement here, the g value, and then it is a function of the sine omega t. This is the g. Now the total displacement will be ug plus u, and ug is computed as this one, the ground displacement plus the u that is computed in the previous equation. So this comes out to be the total displacement, and the amplitude of this total displacement is gamma rather than xi sine of omega t minus gamma, not phi, because now the total displacement is the sum of the two functions. So therefore in ground displacement, the u will be gamma will be used in as a phase angle. And now the this amplitude, the gamma, can be computed. Gamma is basically the amplitude, and that is the coefficient, this part. So this is a gamma, the amplitude of the ground vibration, and this is the phase angle. Now, how much force is the what is the ratio of the amplitude of the ground displacement to the mm, total displacement to the ground displacement? So that is the transmissibility. You want to see the ratio of the displacement of the structure to the displacement of the ground. So xi over g, the amplitude of the ground vibration over g, this is called as the transmissibility. And similarly, the force transmission, that if there is some force is applied but there is no ground motion, then how much force is transferred to the ground. So the two forces which are responsible for the transfer are the damping force and the spring force. So Cu plus Ku, and then solving this problem, taking the velocity and the displacement, and this is the force, total force that is transferred to the ground, and the ratio of the total force to the static force P naught over K P naught, that gives you the transmissibility function, the ratio of the amplitude of the total force transmitted, that will be Ft, and the transmissibility is the ratio of the Ft to P naught. So this transmissibility can be computed by this expression. And then we discuss the different problems related to the harmonic motion. So based on that, vibration measuring instruments are made. There is acceleration measuring instrument and displacement measuring instruments. Vibration measuring instrument is very important in structural engineering because you know that whenever the earthquake is to be measured, vibration of any structure is to be measured, vibration of any machinery is to be measured, measurement of the ground motion, building motion, and also for the laboratory testing. The vibration measuring instruments plays a key role. These are also called as the seismic instrument in the civil engineering and highly developed and the intricate because a very delicate instrument. And underlying principle is simple, the spring mass damper system. You can see the system. This transmissibility effect is basically used, and the spring mass system is basically installed into these system. Here you can see that this is a inside this equipment is a spring mass system. So spring has the mass, the damping, the U value, displacement that is to be measured, and the K value. So when the subjected to the motion, any ground is subjected to the mass moves. So the mass moves and the motion is recorded after suitable magnification, and the motion can be recorded. So basically the ground motion, how much force is transmissibility plays its role. The ground motion was there, and how much the force ground motion is basically transferred to the system. What was the properties of the system? So it means that transmissibility function can be computed, and based on this stiffness and the damping, you can get a certain idea that this much was basically the motion. The relative motion can be computed. So different instruments are required for seismological observations and earthquake engineering measurements. For example, the measurement of acceleration now, you can see here the principle also and how these are basically used. The spring mass system, and basically you know that the ground is subjected to the acceleration u g dot dot. So let the sport move with the harmonic acceleration given by, if the sport is moving by the harmonic acceleration, that is equal to a sine. Let's say a is the amplitude of the acceleration, and sine omega t, you know that the function of the ground motion, basically harmonic function, it can be sine or any other time dependent function. And you know that the displacement response in case of the harmonic motion can be written in simplified form as this one, rho sine omega t minus phi, and the phase angle is equal to the phase angle that we have studied already is, in case of the harmonic motion, is 2 zeta beta into 1 minus beta square, where beta is the frequency ratios, and the rho value is equal to, now if you compute the rho value, here it is a is used rather than p naught, a is used, because now it is the acceleration response. So therefore, not the force, basically for harmonic force, but harmonic acceleration you can say. So therefore, rather than p naught over k, it will be a over k and m, and then putting the values, the rho is basically the amplitude, that is equal to this one, and further simplifying it, it comes out to be, we know that k is equal to m omega square. So putting the value of the k as m omega square, and m is cancelled. So this is the answer of the amplitude. Now this is the ratio of the amplitude and the Mayer displacement. As I told you that this is called as the transmissibility function, and how you can compute that rho over a, the amplitude of the, basically the total system, and the amplitude of the given to the this acceleration, the ground acceleration. This is the ratio is computed by this formula. So if you set the, now this is the relationship that will be used to compute the transmissibility, and the ratio is dependent upon the frequency ratio. We have to set what was the frequency ratio of the our ground, and what is the frequency of our mass spring system. We know the damping value, and you can compute the this ratio of this value, and similarly you can compute the rho amplitude, and if you know the peak acceleration, you can compute the total amplitude of the spring mass system. The ratio is dependent upon the frequency ratio, the frequency of the ground acceleration. So in this way, by using these expression, the vibration measuring instrument analogy is simple, and this analogy is used for the measuring the ground acceleration and the response of the system. But the point is that if you plot the magnification and the frequency ratio, if you plot it, and you have studied it, that if you plot this magnification, since the ground motion due to earthquake is having different frequency content, ground motion is not a constant frequency content, it will have a different frequency content. So the measured response should be independent of the frequency of the ground motion. At the moment you see that the ground motion frequency is playing an important role here, and but it is varying for earthquake. So it means that rho omega square a, that you studied this expression, this one, rho into omega square over a, that is dependent upon the beta. This is depending upon the beta. But it should not vary with beta, because if the beta is too much, variation is there in the beta. So therefore, you can plot the frequency ratio in this initial range, beta from 0 to 0.6, the psi value of damping 0. These are the answers for the rho omega square over for 0.7. It is very closer to 1. You see that the psi, again, when the these values are taken, these are very closer to 1. For psi 0, the phase angle is 0. All phase angle are 0, and for psi 0.7, the phase angle are same. So it means that initial part from 0 to 0.6, 0.5 you can say, 0.5, 0.4. The values are closer and closer to 1, and rho megasquare over A almost remains constant. Here A is the amplitude of the ground acceleration, and rho is the basically the amplitude of the system, and omega is, you know, that the frequency of the system. So we know these parameters remains almost constant, but when, if you want to compute it, then what is the ratio when it remains constant is initial part only. In the initial part of the beta less than 0.5, these are constant, and for zeta equal to 0.7, these are mostly for this damping ratio. If the error is not more than 5%, so for this damping ratio of 0.7, we can say that our and for the beta value of 0 to 0.6 approximately, these values remains constant. So for the vibration measuring instrument, we have to set these values, the damping ratio C in such a way that it should be less than that. Then you can basically use that, because in other case the frequency is too much varying. So so you can see that basically by setting these values of the beta and the zeta, you can basically measure the ground acceleration. So since this amplitude is inversely proportional to the frequency of the system, the rho over A is inversely proportional to the frequency of the system. Mm. High instrument frequency will result in low magnification and therefore must be magnified through some other means. So basically, if the frequency is high, then it will be low magnification. Rho will be rho. Basically, this is the transmissibility rho over A, and or here it is terms are used as the magnification, and therefore must be magnified through some other means. So we can magnify this through some other means, just not only depending upon the frequency ratios. So the time shift basically, this is also interesting that between the Mayer response and the ground motion response, the time shift is given by Ts is the ratio of the phase angle, the change phase angle to the frequency of the ground motion. So you can say that putting the value of the phi here, phi is known, tangent inverse this, and 1 over gamma. This is called as the time shift, the ratio of the phase angle of the system to the frequency of the ground motion. So by putting the values, you are getting this one. Ts is the time shift. So Ts divided by the regular time period. So this is the ratio of that, putting the value of the T T, because omega is replaced by the 2 pi over T. So T comes out here, and it is equal to this one, 1 over 2 pi beta tangent inverse 2 zeta beta, or 1 minus beta square. And when the motion being measured is harmonic, the shift is of no particular significance. So if there is a regular harmonic motion, the shift is not significant. But in case of the earthquake, you know that when the blue color line, when there is a damping ratio is also 0 for the different value of the damping and for the different values of the frequency ratio. If the frequency ratio is from 0 to 1, it's not significant. If it is 1, then it is like that. Behavior of the time shift Ts over T is like that. But we see that when the motion of the several harmonic component, like a haphazard haphazard basically motion is there where there is a seismic waves of vibration time history. So this shift will distort the motion of the instrument. So that shift will distort the motion of the for the zeta value of 0.7, it is again seen that the shift is practically constant. This green color curve is for the value of the damping ratio equal to 0.7, the green color curve. So for this part, you can see that the shift is practically constant and the phase angle is a linear function of the beta and the omega. So phase angle is a linear function in this part. So therefore, again, for zeta equal to 0.7 and frequency ratio of about less than 0.6, you can measure the vibrations well. So in this on this system, the ground vibration or the seismic measured instruments are made. And similarly, if you want to measure the displacement, ground displacement, again the transmissibility is used and we can measure the ground displacement. The same principle. You can see here that what is the ground displacement UG? Is G sine omega t. And what is the, it can be written in this form, tangent phi. These are all already known. I have also told you that rho is the amplitude in case of the ground vibration, where G is the basically the value of the ground motion, and sine omega t is the function by which the ground motion is varying. So you can compute the rho as this one, and ratio of the rho over G is the transmissibility, and it is basically given by this one, dividing the rho by G, and the measured motion is dependent on the again the frequency ratio. And when you plot the rho over G and frequency, again you see that here in case of the ground motion measurement, these are constant after beta larger than 2. So when you are making an instrument for the ground motion measurement, we have to keep the beta larger than 2.5. In case of the acceleration measurement, the beta was less than 0.6, but in case of the ground motion measurement, the beta is to be kept as larger than 2.5. So you can see here, and the frequency, the larger frequency ratio, uh, higher value of the beta are basically rho over G remains constant, and the frequency of the displacement measuring instrument shall be very low in comparison of the with forcing frequency. Forcing frequency and the displacement measuring instruments will be very low. Such instrument is unwidely because of the heavy mass and the soft spring. So we can make a instrument by with heavy mass and the soft spring. But for the high value of the rho over G, it's almost unity value, and the phase angle at 180. So we can apply this function to measure the value of the ground displacement. So this was about the general one, that how we are measuring the ground vibrations and the ground acceleration, and what is the basic philosophy for the measuring these. Now based on that, the instrument that which are developed are The vibration measuring instrument which are basically used. These are the accelerometer which are built on the same principle. You can see here that system, the mass is there, the spring is there, the damping is there. So all are basically visible on that cross section, but we are not much interested in the deep uh, making of this, but application of this instrument. So normally internationally these equipment are installed in the building. Uh, you know that the mass is proportional to the acceleration, and this is one of the force balance accelerometer. These are small equipment and can be attached to the buildings, and the building code, international CBC, California building code require at least 3 accelerometer should be installed in any structure if the floor area is larger than 5,000 square meter or over 6 stories. Building is more than 6 stories, so you need to measure these by the force balance accelerometer. So this is the measurement of acceleration by the force balance accelerometer. Then is the piezoelectric accelerometer. That is the another type. These are the crystalline materials, piezoelectric, and generate the current when strained, and strain when voltage is applied. When the voltage is applied, then the strain is basically developed and can be used with the proof mass to generate an electric current proportional to the acceleration. So electric current is linked with the acceleration, and this cannot detect the static acceleration or field gravity, but these are mainly for the vibration acceleration, which is basically for the building vibration. So piezometric are also commonly used. And then is the some other acceleration which are MEMS based, with these are cheap accelerometer and developed by the electrical engineers. Even some MEMS technology is used. The MEMS stands for the micro electromechanical systems, and these accelerometers are basically used for creation in this accelerometer mechanical structures, creation of the mechanical structure only micrometer in size on silicon wafers. So these are produced, and the cost advantages there more accurate and sensitive sensors these are, and unit cost is also less. So we can also integrate these sensors and the digital circuit, because these sensors, these accelerometers are not only for the building but for the computer data center. It is also installed, and because anything for very critical electrical installations, for critical atomic installation, so these are installed. So these definitely we have to, lot of accelerometers are needed in the structure which are sensitive structures, car industry, heavy mechanical industry. So these are the some are the analog based devices. Here you can see some of that chips, just for general idea. These are not very large equipment, and nowadays the wireless equipments are also there, where you can install these chips on the bridges and you can monitor the data from the office that what is the vibration. Of course, the sensitive instruments are costly, especially when civil engineering structures, where the time period is basically small, and for smaller values, we have to see that what is the critical and the sensitivity and the precision of the equipment required is high, because the ratio normally for any vibration measuring instrument, we have also in the department laboratory, the values are given that what is the frequency range, what is the range of the linearity, dynamic range. So we have to see that, because the equipment that is measuring the machine vibration is will not be able to measure the building vibration. So the sensitivity should be lying with that range. If we should know that what is the hour frequency of the building and what the value that we are interested, because the machine frequency is quite high, but the building is very small. So therefore, based on these, we can select the accurate equipment and a instrument which can be used to measure the vibrations of the building. So this was the first part of the today lecture, where we discuss about the transmissibility, the force transfer to the ground and ground acceleration transfer, building, how much effect of the ground acceleration on the building, and the basic philosophy of the developing these vibration measuring instruments and the vibration measuring instruments. The next part we will discuss about the ETABS time history things, basically what was the application of this chapter, and the time history analysis also we will discuss in the next part. And the energy which is absorbed in the viscous damping, that we will also discuss.